Welcome to this presentation where my intention is to add some color to the way in how Xilinx is delivering to its vision of being an essential building block to the composable data center. And, to start, I would like to perhaps go back a little bit in history. And for some of you who are listening to this presentation and haven't looked for a while to FPGAs, you probably have some memories of the FPGA being the alternative for ASIC design and being an ASIC replacement. And the typical software that was used to design for the FPGA was catering to the traditional hardware designers using, register transfer level design tools to program these FPGAs. Now, as we moved forward during a second phase, FPGAs have more and more been used as an accelerator that is kind of a subordinate to the CPU. And the software to program the FPGA is now written in a higher level language like C or C++, but still requires good understanding of the hardware architecture. So in many cases, people are not really referring to this as pure software design. It's kind of hardware software co-design. You have to have a good understanding, of the hardware architecture. And I would say traditional software people can, in this phase, unleash the full potential of the FPGA accelerators by leveraging, applications that are being built in appliances or applications that are being pre-built into the cloud that are using the CPU combined with the accelerator. And they can have access to this platform using the higher level frameworks. So a third phase is where the FPGA is not just an accelerator that is a subordinate of the CPU and that is controlled by the CPU, but the FPGA is becoming a programmable compute fabric that has been kind of elevated to the status of a peer building block to the other compute fabrics that are being made available in the data center. And these compute fabrics are like the CPU, that is a scalar sequential processing unit that we are all very familiar with, the GPU that is very well equipped to target vector processing, devices like TPUs that are focused on matrix processing. And then you have the FPGA, which is kind of a programmable data flow architecture, whereby the data movement is programmed explicitly and can be very efficient, which is a very important characteristic in the era where data and data processing is becoming an essential part of the performance of your overall system. Because to a large extent, this evolution is driven by the requirements of the data center that are now catering to these new workloads driven by machine learning, whereby the users are becoming the data scientists, right? So that's a little bit the trajectory we have been going through the FPGA in the FPGA world, and how FPGAs are now elevated at this level of a peer essential building block in building effective data centers that cater to the workloads of the future. So when you look at, we all know that, and it was referenced before, Moore's law is slowing down. These new requirements of data centers are driven by characteristics, in many cases, of the data, the velocity of the data in terms of, the throughput of the data that's required. Just think about video coding, but also the latency it also deals with the volume, the sheer size of data, the amount of data that has to be processed. And then finally, also the variability of the data. I mean, and the unstructured nature of the data that a lot of workloads have to deal with. And so all these characteristics have led to the recognition that, the CPU is falling short in keeping up with the growing demand of compute power and the massive data movement requirements that are imposed on the data center. And this results, first of all, in the emergence of more specialized accelerators to be able to continue to scale up the performance of a specific compute node. So you create a heterogeneous compute node. And this allows you to continue to, within a node, create a higher performance, despite the fact that Moore's law is slowing down. And in these kind of scenarios, the compute, or many of the compute functions, are offloaded from the CPU to specialized accelerators. In these cases, in many cases, the CPU is the host, and the accelerators are connected as kind of I/O devices over PCIe with their own personal memory. Now, a second important trend is that, especially driven, as I said, by some of the applications such as search, graph analytics, machine learning, the workloads of today and in the future are scaling out way beyond the capability of one compute node. They scale out to hundreds of nodes, to serve up one application. And the introduction of the SmartNIC enables this scenario to be implemented in a more efficient way by providing the opportunity to create dedicated network topologies, dedicated protocols, and higher bandwidths and lower latency by offloading some of the connectivity functions from the CPU to what we refer to as the composable and programmable SmartNIC. And that programmability, that includes protocols that are tailored to an application, topologies that are optimized for specific workloads and data flows, protocols that are tailoring to specific figures of merit, such as latency, robustness, security, and then specific data movement patterns, like nearest neighbor or crossbar or star connectivity. A good example of that is, for example, Slingshot or HPC Ethernet that is targeting specific requirements of the high-performance compute world. So it's important that we believe that the SmartNIC is becoming an essential enabling building block that allows all these different nodes in your network to communicate via dedicated protocols. There will be a follow-up video that will go into more detail about what is the unique capabilities of the SmartNIC and what are the capabilities in the FPGA that allow us to build these programmable and composable SmartNICs. Now, giving all that, when we go back now to the specific of a compute node and how do we continue to improve the performance of a compute node, given the fact that we know that Moore's law is not going to deliver all these these improvements anymore. I was talking about the use of specialized accelerators enabled by programming FPGAs or other dedicated silicon. Now, traditionally, in many of these scenarios, the the CPU is still the host of the node, or the master, if I can say so. It is everything, has to pass in the node through the CPU and is controlled by the CPU, such as all the communication between the accelerators, the access to each other's memory. All of that is traditionally controlled through the CPU. That makes that the CPU is becoming the communication bottleneck. And next, it's therefore to provide the accelerators with the same capability as the CPU and allow them for real dedicated peer-to-peer interconnect and shared memory between all of these compute fabrics within a compute node, such that you do not need to go through the CPU if not really needed. The data and the results are communicated through shared memory that in many cases can be cache coherent. And protocols such as CXL have the intention to target such use scenarios. And the programming environment for such a compute node is evolving, leveraging new formalisms such as OpenCL, HIP, SYCL, that support the heterogeneity of a compute node, the parallelism of the compute node, and the shared memory characteristics. And these programming mechanisms allow you to orchestrate the compute kernels that are executed by the accelerators. So now the efficient handling of data movement in many applications is essential to reach the performance. And the guiding principle there is also to avoid moving data by having the compute capabilities alongside the data storage devices. And so one example is, placing some of these advanced algorithms or advanced database access and search functions close to the SSD. And Xilinx definitely has led the way there by coupling the FPGA close to the storage to provide, for example, configurable and flexible SSD management or bump-in-the-wire compression. Whereas the scale-up of a node is enabled by these peer-to-peer memory fabrics that give the different peers access to each other unified and shared but distributed memory. The scale out is achieved by the SmartNIC that allows to implement application optimized protocols. And combining now the evolution in the scale up and the scale out of the data center will allow us now to build an adaptable and a composable data center whereby the building blocks are all peers of each other. And this architecture allows for specialized compute servers, customized storage servers, and disaggregation of resources. And this allows better scaling. It allows better provisioning of resources to meet different application needs. And beside a more efficient utilization and the customization of the resources, the FPGA is equipped to perform computing on the data in motion as the data is streaming through the SmartNIC rather than waiting until the data is at rest. A good example of something like that is aggregation across the results of distributed algorithms on multiple servers. This is a unique capability that is enabled by the data flow architecture of the FPGA. And Xilinx has been pioneering this new breed of SmartNICs to support these capabilities where the FPGA have tightly coupled network functions acceleration, but also streaming data compute acceleration, which gives the basis for the in-network compute. Another example can be of this scenario can be, for example, sophisticated machine learning algorithms that analyze the data as it is streaming through the NIC, and it analyzes this, with very low latency, and it thereby guarantees a higher level of security of your overall data center. The second thing, besides, accelerating compute on data in motion, compute on data at rest means that the computing is performed close to the storage. And rather than wasting the energy and time by transferring the data from the storage to the CPU nodes, several compute tasks can happen close to the storage. And finally, there is the computing of the data in use that is distributed in the memory of the different compute fabrics. And looking at this architecture from a different perspective shows how the resources of a data center can now be disaggregated and the appropriate fabrics can be allocated to different workloads. So when you combine all these capabilities, right, the capabilities to accelerate data at rest, data in motion, right, and data in use, the capabilities to program your SmartNIC for dedicated protocols and dedicated topologies. This combination of all these technologies, you start seeing, the true benefit of FPGA technology to build an adaptable, composable data center. You can assign a compute-heavy workload to a group of accelerators that are interconnected by an adaptable and intelligent fabric. That fabric can be, programmed and adapted to the specifics, of a workload. So now, in order to unleash, that full capability, you have to make sure that you give access of that capability to the software people. And therefore, it's very essential that, we provide a software stack that can program the compute accelerators, that can program these smart NICs, program the smart SSDs with the optimal acceleration algorithms, and then provision and compose resources in the right numbers for each workload. And also there, Xilinx has, really introduced a whole new plethora of software capabilities under the umbrella of the Vitis Unified Software Platform. This platform was introduced in the first time around 2019, and it provides now a comprehensive software stack with libraries that cater to computational storage, network acceleration, machine learning, that provides the basic programming tools from compiling from high-level languages, C and C++, but also including SYCL and HIP, and the necessary runtime for a specific target platform. It is integrated with domain-specific application frameworks for machine learning like TensorFlow or video processing like FFmpeg, so that application programmers can continue to work at the level they are familiar at without having to be exposed to the complexities of the FPGA architecture. And one of the specific recent introductions was also, the introduction of the P4 programming flow to support the acceleration of our packet processing in the SmartNIC. So P4, as you all know, is a domain-specific language that is used in the industry for programming packet processing, data planes, in network devices. And so this is a very important high-level capability that we introduced recently in Vitis. And then lastly, of course, we see a significant role for high-level resource provisioning and composition frameworks to help with the intelligent resource allocation. So all of this is augmenting, I would say, the traditional FPGA design flows to cater to that scenario of the composable data center. So in summary, I would like to highlight some of the key differentiating factors of the FPGA technology and why it is an essential building block to create that future data center that can deal with the challenges of the workloads that are coming towards us, that are driven by massive data processing and massive data movement. And the first, key aspect, of course, is the adaptability of our architecture. We have a data flow architecture that, provide the capability to customize data flow processing and the memory architecture. Given the fact that data is so much dominating in how efficient computing happens, that's a key capability of the programmability of our architecture. It is adaptable. It can help in scale up of compute nodes by providing shared distributed memory, extending the memory, for all the different nodes in a shared, unified way. It enables the scale out of your network optimized for a certain workload, be it a figure of merit that could be latency or that could be robustness. You can focus and tailor your connectivity on that. FPGAs are essential to provide converged acceleration of data that is in use, leveraging the high bandwidth unified distributed memory fabric, acceleration of data in motion by the in-network compute, leveraging the data flow architecture of the FPGA. And then, of course, accelerating the data at rest by providing the capability of near storage compute. And then ultimately, we believe that the FPGA is the essential building block towards enabling the disaggregation of the data center architecture by supporting customized connectivity of optimal resource configuration.
You depicted a very interesting scenario for the future, and it is common to other vendors like sharing memory across server and things like that. So CXL is really a big enabler. But the difference is that memory is a static component, while FPGA is programmable. Okay, so what is the impact of this activity before using and releasing the resource in this kind of scenario? I mean, I don't know anything about FPGA, so is it just I pass some code, the FPGA is reconfigured, and then I can use it, and then when I release it, it can be reprogrammed again, or is it more complex than that?
Yeah, no, it's pretty. The way you can look at an FPGA, there are two components when you talk about memory. There is the program memory, and there is the and there is the data memory, of course, right? So the FPGA, from a programming perspective, can be reprogrammed, in exactly the same way as a CPU. So from a conceptual point of view, at the higher level of operation, a software person doesn't sees any difference there, right? Now, on the data memory side, one aspect of programming an FPGA is not just programming the sequence of instructions that it is executing, but you can also program, how your memories are connected. And so an FPGA has different granularities of memories. An FPGA doesn't have, for example, cache memories, right? So, and that's that's good and bad. The good thing is it gives much more efficiency to the FPGA. The bad thing is you have to explicitly every time program, the data movement, and that makes the compiler, has to be so much more intelligent to be able to program all these different configurations of the memory and explicitly program the data movement, right? And so I think that's where we made so much progress in the recent history is by, creating a compiler technology that really takes away that burden, of an architecture that has a much higher potential, but also has a much higher complexity in being programmed. By improving the quality of the compiler technology, we have taken away that burden. And now we have really software people that can leverage the full potential of that FPGA architecture. So that's how you should look at it. In a simple way, you can think about an FPGA is you have an extra degree of freedom in implementing your solution to your problem, whereas a traditional CPU, you have a fixed architecture and you write a program and you compile to that architecture. With an FPGA, you have an extra degree of freedom, which is you do not only compile to an architecture, you can also adapt your architecture to your problem at hand, right? So, and that's, I think, where the performance comes to a large extent from the FPGA.
You mentioned on there were a couple of slides there where the interconnect was Ethernet. That's what it looked like to me. So is that what you're targeting as the main Ethernet, or do you imagine that there would be other interconnects between, say, FPGAs? You have FPGAs, but you've got SmartNICs connecting to memory devices, connecting to storage devices. The alternatives that we've seen in other presentations during Tech Field Day was CXL, for example. How do you see those working together, if at all? Yeah,
that's a very good question. And I think that's one of the things that I wanted to highlight. And so the great thing about an FPGA is that it is programmable hardware, which means you really can program, the protocols in the FPGA. So Ethernet is just one of the connectivity standards that the FPGA supports. In another slide I talked about CXL. There are proprietary protocols that we see some people are using for the connectivity. So that's actually one of the major benefits of the FPGA. Now, of course, you have to in many cases you have to live with the existing infrastructure, and you can overlay things on top of that infrastructure. And so that an FPGA allows you to do that. It allows you to also out of band communication. So I think from a connectivity perspective, FPGA provides you probably with the most flexible platform, to adapt to whatever is your preferred connectivity protocol and topology.
So, Ivo, I thought the one, the diagram that you have showing kind of the traditional kind of server architecture and then a CXL enabled architecture were really good at showing, kind of illustrating kind of the difference in the paradigm shift that's going to give to kind of composability within that structure. Is there anything you can elaborate on ways in which you're using CXL to basically, make your SmartNIC, the transfers more efficient between, the other CXL enabled devices within a system?
Yeah, well, one of the key aspects is that in this scenario that I was sketching, we consider the the accelerator be equipped with all the same capabilities as traditionally the CPU. So in other words, the accelerators have a kind of a unified access to the distributed memory that is distributed over all the different accelerators. And that includes the memory in the SmartNIC, right? So that is going to create a tremendous amount of efficiency because you will now avoid a lot of unnecessarily copying of data and transferring data back and forth. So that's one of the capabilities. Of course, the other thing is the bandwidth, right? That is being provided. So, but I see that as table stakes, right? We have to keep on improving the bandwidths and so on. But I keep on saying this, and I think it's really an important aspect is accelerators are becoming the peer of the CPU, right? And I can perfectly see now headless nodes, right? Where there might be even nodes where you don't even have a CPU, right? And I clearly envision that future potentially. And so that's essentially enabled by this kind of connectivity.
That's a very bold statement, Ivo. If by your words, can I get you to understand? Do I understand, or should I understand that you're saying that in the future, in the very near future, we will see all the processing being done on an FPGA without a CPU being out there arbitrarily providing power?
Well, that's a pretty extreme statement. I CPUs, of course, are an important component in the data center and will stay like that. But I can imagine, I not imagine that there are applications where, in all fairness, you might need a CPU to set up your overall configuration of your multi-node compute, but then the CPU is basically getting out of the way. So the CPU is kind of the potentially the control functionality that sets up, the configuration, and then the computing and the data movement all is being executed by the accelerators. In this case, the FPGA, right? There is no need for the CPU to intervene with the computing. The CPU might be there as a convenient capability to set up the architecture.
Basically, I'm sorry about that phone call thing. Basically, the CPU will be acting as sort of the traffic cop. Is that it?
Yes, but not real time. The CPU would kind of statically configure everything, and then what you potential and then fire off. I'm trying to simplify it here a little bit, but then fire off the compute and stay out of the way. Now it could be that occasionally, a task is dispatched to the CPU to do some, on the side monitoring of things, but I think most of the compute would be into a network of connected accelerators. A traffic cop is perhaps, but not real time. I mean, it would be like occasionally would be intervening. Yeah.
Oh, thank you.